All right, so in this lecture we are going to look at the following. Oh yes, I know what you did last summer, some of you anyway. It was this exam, February 09. Now this isn't in your course pack, okay? I've made sure that this isn't in your course pack. So what we're going to do in this lecture is do question 3, and then in tomorrow's lecture we'll do question 4. So we'll do the whole course in 2 lectures basically. All right, now don't worry about copying this down. I'll post it on YouTube with some photos and stuff, so don't scramble writing it down now. I'll also write down the basic gist of the question in my solutions, so don't worry about writing this down, okay? Okay, so now, 2 questions, at least in this test, there's 2 questions on calculus and 2 questions on algebra, and they're separated. Now, I have seen some exams where they're mixed up, but I'm just going to sort of call it like I see it on this one. So, question 3. We've got an integral involving powers of cosine and sine. Now this is going way back to section 2. Can anyone suggest how we might tackle? Even simpler than that. Even simpler than that. Well, I guess we are going to use some sort of substitution at some point, right? With cos squared and sine squared and things. But you're saying break up the cos cubed, right? The odd power. Is that what you were going to say? Yeah. Yeah, so, I mean, you know, you can probably do these a number of ways, but let's break up the odd power. So take a cosine out of the So, is that what you were actually saying before? Okay, all right. So what now? I'm confused, I've forgotten. I'm in holiday mode already. Yes? Oh yeah, why? Why would you want to change cos squared to something involving sine? That's right. That's it. What we're trying to do now, get everything in these big brackets to a sine, something like a power of sine. Okay, so I've pulled a cosine out. I want to get everything else a power of sine. So I can use either the substitution or just do it by inspection. So if I expand inside the big bracket, I'll get something like this. So I'm at a pretty good place. What I can do now is do one of 2 things. I can either just do it by inspection, right? Or if I wanted to formalise it, I could make a substitution. Okay, so the way I'm going to do it oh, sorry. The way I'm going to do it involves this boxed formula. Okay? Now, if you do want to go through and make a substitution, what would the substitution be if you wanted to solve it, integrate by substitution. U equals what? Sine x, right. So there's two ways of doing it. So what I've got here, if I expand this, I've got two different cases of the following. That's it. Okay. Now, if you want to use substitution, you can, but it's just going to, I mean, it'll slow you down. You don't really need it. You should be able to know what the integral of sine squared times cosine is. Questions? Yes?
Will there be a penalty if we get the constant integration?
Probably a small one. So the question is, what about this constant integration? If you leave it out, yeah, you'll probably suffer a small penalty. Yeah. Any other questions? Okay. All right, so the next question, again, don't worry about copying it down, is to integrate this. Partial fractions, right? Partial fractions. So I'll put this up in a second. Okay. All right, now, this is a little bit harder than what you saw on your class test, right? Why is it a little harder? Because there's an x minus 2 all squared. Okay, that's the thing that makes this a little bit trickier. So what I'm going to do is find constants a, b, and c such that the integrand can be split up in the following way. Okay, how have I done this? Oh, yes. Now, of course, you could have those three terms arranged differently. You could have a on x minus 2 plus b on x minus 2 all squared plus c on x plus a. That's fine. I've just chosen to do it this way. All right, so how do we do it? Well, I am going to multiply this by everything down here. Okay, both sides. So I'm going to get some cancellation. Yes? Good question. The question is, why do I just have a c here rather than a cx plus d? Anyone know? It's a good question. Hands. Anyone know? Yes? I guess it's got to do... Well, I mean, you could have cx plus d, right? But you're going to get c equals 0. It's not necessary. I'll show you why. This, x minus 2, is linear, right? It's, let's say, a linear function, right? So what's the... You want this, what's up here, to be 1 less than the highest power inside this bracket. So the highest power inside this bracket, x to the power 1, right? So what's the next power down from that? Power 0, which is just a constant. If there was an x squared in here, if it was x squared minus 2, then it would be something like cx plus d on top. Okay? That's a really good question. All right, so, yes?
A on x plus 1 plus bx plus c on x minus 2 squared. And then do comparison with coefficients.
No. Because if you expand that out, you're going to get something like bx on x minus 2 all squared, which I don't think is going to give you what you want. You need two. I guess you need two two terms here, right? Okay. All right, so anyway, let's multiply both sides. So basically we're taking this and pulling it up there and multiplying through by each term. All right, so on the left-hand side, I'm just going to get that. So this is going to cancel out when I bring it to the other side. One of these is going to cancel over here. And then the x minus 2 is going to cancel when I bring that over here. Yes. Yes. Now, I'm confused. What do we do now? It looks like a big mess. Yeah, let's sub in some values of x in that bottom line and see if we can get our a's, b's and c's. Because once we have our a, b's and c's, we know we can integrate each of these terms. Okay? That's the idea. So, x equals 2 is a good choice because that'll disappear, and we'll get this. So on the left-hand side, I'm going to get something like 10 minus 4. That's going to be 0, that's going to be 0, that's going to be 3. So what's c going to equal? 2. So what's another good choice for x? Minus 1, right. So if we put in x equals minus 1 in here, that's going to disappear, and we'll be left with that. Okay, so on the left-hand side, we're going to get something like this. So 0, 0, we're going to get something like 9a. So a is going to be minus 1. Now, how to get b? Yeah, x equals 0 is a reasonable choice. Okay, so on the left-hand side, I'm going to get minus 4. Over here, I'm going to get 4a. Over here, I'm going to get minus 2b. And over here, I'm going to get just 1c. Now, I know what a and c are. So I can just plug those in. And then just rearrange. So what's b going to equal? 1, I think. All right? Yes, that looks good. So now what? Well, let's plug them in and integrate each term. We know what these constants are. So let's integrate here. So a is going to be minus 1. B is going to be 1. And c is 2. So I can integrate both of those. The first two are going to give me logs. The second one's going to give me something like 1 on x minus 2. Something like that. Now notice I've used a constant k here rather than c because I've already used c up here. Okay, small, but you want to be careful. You don't want to give the marker a chance to take off half a mark when they don't, when they don't have to. Now, do you need to clean up the logarithms? Probably not. You can if you want to, but I don't think it's necessary. Questions? Yes. Yep. Unlikely. This is not a guarantee. Not a guarantee. Unlikely. Yeah. This is probably as hard as it'll get. Yeah. Any other questions? Yes. About simplification? You could. Okay, that's a good question. The question is, how much do you have to simplify your answers? Okay, I'll give you an example, right? I marked a class test and the student left the answer as something like, 2 on 10 times 3 on 5. That was their answer. Okay? And they're like arguing with me. And I'm like, no, you got to simplify your answers. If there's simple calculations, you want to simplify them. Okay? But for this is okay, I think, to leave open. So if it's like, simple fractions or something like that, simplify it definitely. But that's okay. Any other questions? Okay. So we're on to ODEs now. Oh, DEs. Now, differential equations are not hard, although some students think they're hard. They're not. So let me show you how to attack these differential equations. This is a first order linear initial value problem. So let's have a look at it and see how we solve it. So again, I'm just going to write down the gist of the question. So remember, with differential equations, it's like any other kind of equation. We are trying to solve it. But the difference between these kind of equations and the one that you saw at, say, school, we're looking for a function here. The solution is a function y of x in this case. So how do we tackle these linear problems? What's the basic idea? Anyone remember? Integrating factor and the product rule. That's it. Okay, you want to form an integrating factor. Come on, man, it's week 12. You don't sleep in my class. I can just see you now. Woke me up in cat-eye. Woke me up too many times. Anyway, integrating factor and the product rule. That's all it is. Now, first of all, let's actually recognise that this really is a linear problem. Here, this is the initial condition over here, but this is linear. So our differential equation star is linear. And you probably don't have to write all of this down, but you have to definitely recognise and say that it's linear. Now that P of x and Q of x are important because they help us to find the solution, right? The solution depends on what the functions P and Q are. All right, so let's form the integrating factor for this problem. So the integrating factor is just the exponential to the integral of p. So here's our p here. Now, students sometimes underestimate how simple it is to simplify this integrating factor. Just be careful. Don't be too hasty here. When you integrate this, we're going to get something like a logarithm. Now, I don't need a constant of integration there. You can put one in if you want to, but that constant of integration is just going to cancel out at the end of the problem. So it's not necessary to have a constant of integration here. All right, so the question is, how do we simplify this? We've got an e and a log, they should kind of cancel out, but you just have to be a little bit careful. Okay, so I'm going to write it like this. And then bring the 2 up there. Now, I can get rid of those absolute value signs. So on the bottom, I've got e to the log, so that can cancel out, and I just get this. Remember, e and log cancel because they're inverses of each other. They cancel each other out. All right, so now what? We found this magical function, the integrating factor. What do we do with it? Multiply, right. Multiply both sides of star, the ODE star up top, by the integrating factor, and then you collapse the left-hand side down to the derivative of a product. Now, it looks a bit messy, but that left-hand side can be collapsed by the product rule to the derivative of v, the integrating factor, times the unknown function. So we get something like the following. Oops, can't spell. Now the left-hand side is quite messy, but just remember, what you should have here is always ddx of v times the unknown function. ddx of the integrating factor times the unknown function. So sometimes you don't even write this line in. You just go straight to here. That would be perfectly fine. Okay, so now what? Integrate both sides, right? We know how to undo ddx, just integrate. Side, I'm going to get y on x plus 1 all squared. On the right-hand side, I'm going to get this. So this is going to go to something like, what's it going to go to? Something like 3 on x plus 1 with a minus sign there. And now all I need to do is make y the subject, bring that to the other side. So I bring that over there, I'm going to get something like this. C equals constant. Now we're not quite done yet. How can we find that constant C? The initial condition, right? We can't forget about that initial condition up top. So here we had that. We haven't used that anywhere in the proof yet or in the solution. So let's use that. So let's set this equal to 2 and plug in x equals 0. Okay, so plug that in, we'll get that. So what's our final solution? Well, we just go up here and plug in c equals 5. Questions? Right, the next part of this question is a second order problem. Second order, right? It's two parts to it. How do we do it? So just bear with me, I'll write out the particular equation. Now I'm just going to do dashes instead of the d dx and d squared. All right. Again, I've forgotten. What do we do? Oh yeah, the characteristic equation, yes. So we break the analysis down from a differential equation to a quadratic equation. So let's give this a label. You guessed it, star. Okay, so what's our characteristic going to be? It's going to be lambda squared plus 6 lambda plus 9 equals 0. So we want to solve that quadratic equation for lambda, find the roots, right? And we can either factorize it, complete the square, or maybe apply the quadratic formula if you really want to. Here we can just factorize. So our roots are going to be -3 and -3. So now the analysis changes. What kind of roots do we have? Well, they're both real numbers, they're both -3, and they're equal. This influences the solution. So what's the form of our general solution when we have real and equal roots? Well, it involves exponentials, but remember you've got to multiply one of the exponentials by the unknown, the independent variable, x in this case, let's say, right? Don't forget this x. Make sure the variable here matches the variable up here. Don't write down bx e to the lambda t. That's done every year. Okay, so the a's and b's are constants. Now, can I find the big A and big B? No, we don't have any initial conditions in this question, so we just leave it like that. Now remember, it doesn't matter where you put the constants. You could put the A over here and the B, you could switch these around. It'd still be correct, right? It'd still be correct. They're arbitrary constants. Questions? Okay, there's a second part to that problem. It involves an inhomogeneous version of this. So we've got a sine 3x over here, and the left-hand sides are the same. What form of the particular solution would you try when solving this? So let's say y sub p all right. what would, if you want to construct some sort of particular solution, what would a good choice be here? Well, it's sort of, generally you look at this and you base your first choice on this function. It's sine 3x, right? However, with these trig functions, sine 3x down here, or constant times sine 3x, wouldn't quite cover it. You need a linear combo of sine and cosine. Now, a good check also when you make this choice down here is to see, is it already contained in here? So if I make this choice, is that contained in there? No. So that would be a suitable construction for my particular solution. Now, you don't have to go through and find the constants C and D. They expressly tell you that you're not expected to find the constant C and D, which saves you a lot of time in the exam, right? So that's pretty good. Questions for that one? Okay. All right, part IV. Again, I know the font's small, so I'll write out the gist of this question. Yes? Yep. Yeah, why not? Why wouldn't you? You can label it elephant, and you know, I dare you to draw a little cartoon elephant in there and circle it. By elephant, we have proved everything. This is a really big result. I'm referring to elephant equation here. No, so yeah, why not? You haven't seen it done before, right? You haven't seen this sort of stuff done before, like with the labelling and stuff? Okay, well, let me tell you, if you label equations and refer to them, your marker will think you're a genius, okay? And it might actually distract them from when you screw up later on. Oh, I don't care, this student got this wrong. They labelled their equations 2 marks, extra 2 marks. Anyway, the point is that, hang on, shh. The reason why I label equations and refer to them is because when you're reading back these solutions, you need to logically put it together. You know, you need to know what step happened where. Okay, that's the reason. It's no good just writing down a whole bunch of symbols and equations and not linking them together with some logical arguments, you know. Setting out mathematics is hard to do. Setting out mathematics well is hard to do. Okay, so we've got a function here. And it's a function of 2 variables. So we're going way, way back to section 1. Now, what does the graph of that function, what type of graph would it be? What surface would it be? Anyone remember? I know we're going a long way back. Yeah, good. Who said a bowl? Yes. Do you know the technical name for it? A bowl's an excellent description. It's very accurate. It's an elliptic paraboloid. I like bowl better though. What we're asked to do is look at a point Q with these coordinates and find the equation of the surface of the graph at the point Q. So so the coordinates are -1, 2, and 12. So Q is a point here lying on the surface. How do we calculate the tangent plane? Well, there's a couple of ways of doing it, the equation of the tangent plane. There's a couple of ways of doing it. You can just use the formula if you want to that involves partial derivatives, or you can use a little bit of, I guess, algebra where you sort of look for 2 vectors that are perpendicular. One lies in the plane and one's perpendicular to the plane. It's up to you. I'm going to do it just the standard way to start off. So suppose this is just an arbitrary point. Now, by the subscripts here, I mean partial derivatives. Now, if you can't remember that formula, that's okay. I'll show you another way of doing this problem without relying on that formula. So here our x naught's minus 1, our y naught's 2, and our z naught's 12. Our big F is this. So let's go through, calculate everything, and so z naught is 12. So f sub x, df dx is going to be what? 16x squared, 16x, right. And df dy is going to be something like 2y. Now, by these vertical lines, I mean this is evaluated at this point. And y naught is 2. Okay, so all we need to do is sub in and clean up a bit. So if you want to rearrange now, you can make z the subject. So that is the equation of the tangent plane. It's not too difficult. It's hard if you don't know where to start with the equation of the, the general equation of the tangent plane. Here? Yep.
Would you have to simplify that further, or just leave it like that?
Oh, I would simplify it further. Yeah, just to be on the safe side. Yeah, I would actually. I would. It's probably not necessary, but I would. Yeah. Any other questions? Yes. Sorry? No. Well, it's going to be. I mean, you could draw the graph of the surface of big F. That's not too hard, but drawing the tangent plane in there might be difficult. If it helps you understand it, though, go ahead. Then everything's cool. Everything's all right. Okay, so let's say you cannot remember this. Okay, so this is the first version. Now, what does the equation of a tangent of a plane rely on? Well, you need a normal vector and a vector in the plane, right? And you dot them, and their dot product 0. That's just from algebra. So how can you work this out? So the normal vector of the surface is just the following. Now down here you can have plus or minus 1 out the front. Okay, I've just chosen one. So if I calculate these derivatives just like before, I'll get that. And so at the point Q, the normal vector, you just plug in here your components for Q in yeah. And now the equation of a tangent plane is just given by the following. Okay, so for us, the point Q is just -1, 2, and 12. So this is going to be something like so remember the dot product, I'm kind of writing my vectors two different ways. I hope that's not too unclear. So what you do is you just expand. So it's this times all of this, plus this times all of this, plus this times all of this. Okay? So that would also be okay. I haven't put all the calculations in there because I want to finish this question before we have to stop. Okay. Aha, the chain rule. Last question on sub-question on part 3. You've got a function involved, w equals g of x and y depend on r and theta. You're given some values here. You're asked to calculate dw d theta at the point P, where P is given here. All right, so chain rule's not that difficult. It helps sometimes to draw a picture. So let's see how we go. All right, so what do we have? So this is the information from the question. Now we don't know what g is. G is some arbitrary function. We don't know what it is. But we do know that it depends on x and y, sort of intermediate variables, and x and y depend respectively on, well, I guess they both depend on r and theta. Now, let's formulate the chain rule. We're asked to calculate dw d theta at a certain instant or a certain point in time. So what I like to do is draw a little linking diagram. So w equals g. G depends on two things, x and y. X depends on two things, r und theta. Y depends on two things, r und theta. So to calculate the derivative that we want, which is dw d theta, we want to find all the paths from the top to a theta. And when I go from letter to letter, I form a derivative. So there's one branch down here and one branch down here. So dg dx times dx d theta. And then you just add the branches, dg dy times dy d theta. Oh, it's a partial. Okay, so what information do we have now? Well, let's actually go through and calculate these. So dx d theta, we don't know what g is. Dx d theta is going to be what? Something like minus r sine theta. And dy d theta is going to be something like r cosine theta. So, at the point P, this is what we know. We know the value of these derivatives. And the value of these variables. So all I have to do is sub this in up here. Okay? So I do for that, minus 1 for that, 2 in there, and pi on 3 in there. So all you need to do is add these up, and you will have a calculator. You don't really need a calculator or a triangle here. You can actually get these values from this information here. Anyway, question 3. Done. Now don't worry about copying all this down. I will post it when I post the video, okay? So don't copy all this down. Just what I'll do is I will incorporate the question into the solution. All right, so question 4 is probably the harder of the 2 calculus questions on this exam. In particular, down here, this is probably the hardest question down here. So we're just going to work our way through systematically and see how to solve these problems. So question 4, we did question 3 yesterday, question 4 today. Question 4. All right, the first question involves a sequence, the limit of a sequence. The sequence is sin n all over n squared. And the question is, what is the limit of this sequence as n gets large and positive, as n goes to infinity? And they also ask you to make sure you back up any methods or claims you're using by naming your methods or naming your techniques. So, I've forgotten, what method could we apply to this particular sequence for its limit? Pinching theorem, right. Pinching theorem. So, now, I'm just going to restrict our interest to n greater than or equal to 1. We're interested in the limit as n goes to infinity. So, you know, that's a good. Huh? Or is it sine squared on? Hang on. Oh, is it sine squared on n? Let me have a look. Oh, it is. Yeah, you're right. Hang on. How's that? Huh? Better? Thank you. Thanks for pointing that out too. All right, so assuming we can copy down the question correctly, we have the following. All right, so sine squared is going to be between 0 and 1. Now that's a basic inequality that you should come to mind straight away. Okay? If not, just go sine n is between positive 1 and negative 1, right? Okay? Cool. And just square that and get that. Now, what I can do now is build this from this inequality. What I want is to have this in the centre. Okay, so I can divide by n. Yep. So what I can do now, hopefully, is take the limit on both sides of the inequality, on the left-hand side and the right-hand side, and I'm actually going to get the same answer. I'm going to get 0 on both sides. So the limit on the left-hand side is just 0. And the limit of 1 on n is also 0. So what do we have? Well, so what's our limit going to be? 0. That's right, because if you have something that's greater than or equal to 0 and less than or equal to 0, it's got to be 0. Okay, so you can see here that I have, it's just one theorem. Oh man, sit all the way. I know you're just going to go back and talk in 2 seconds. Be quiet, please. Yeah, I know. I can just... I've used 3 ways of describing that theorem. The pinching theorem, the squeeze theorem, the sandwich theorem. They're all equivalent, right? Just some people use different words. Any questions? Yes, you had a question. What? Yeah? Oh, how's that? Better? It doesn't matter. It doesn't matter what. I mean, yes, you're right. Technically, you're right. It's still 0, right? Whatever the limit's approaching, it's still 0. All right. So, pretty easy question to start off with. Pretty easy question, right? Let's have a look at some series now. Now, series are probably the part that students struggle with the most in this course. So let's see whether the following series converge or diverge, and they ask you to name any test that you use. So let's have a look. So this is part II. All right, here's our series. Any ideas on what tests or what methods you might apply for the convergence or divergence there? Ratio test. Why the ratio test? Yes, it's got exponents and factorials. So the ratio test is a good starting point here. Now, if the ratio test doesn't work, we have to go back and try something else, right? But we're pretty confident that it's going to work for this. So with the ratio test, it's the limit of a ratio. Okay, that's all it is, really. So let's set it up. So a sub n is just going to be 3n on n factorial. A sub n plus 1 is going to be this. So I'm actually going to simplify the algebra here. Okay, it just makes it a little bit cleaner when I come to doing the calculations. All right, so consider, please. We want to analyse the limit of this ratio. If that limit is strictly less than 1, then the series converges. If that limit is greater than 1, the series diverges. What happens if the limit equals 1? You know, nothing, right? You have to use a different test. Good. All right, so just multiply by the reciprocal and then cancel. So I'm taking the limit of 3 on n plus 1 as n goes to infinity. What's the limit going to be? 0. So let's apply the ratio test. Our series in star must converge. Pretty reasonable. Any questions? Okay, let's have a look at the next series. We've got this. So what kind of series is this? It's an alternating series. Okay, so for that one, what test do you reckon? Leibniz test or alternating series test. It's the same, right? So let's have a look at the alternating series test. So this will be part B. Okay. It really is an alternating series. It's got to go plus, minus, okay? So that one, if you write out the first few terms, it will go plus, you know, the signs will alternate. So for alternating series, we need 3 things to tick off for our Leibniz test, our alternating series test. So I'm going to let u sub n be the little function of n there that's not connected with the minus 1. Can anyone remember what are the 3 things we need to show that u sub n satisfies? It's got to be positive. Say decreasing. And one more. Better not put that finger up. What's that? It goes to, limit goes to 0, right. So there's 3 things with alternating series test. All right. So we have the following. So un is this, which is always positive. So I'm just going to say for all n, say greater than or equal to 1. That's good enough. Okay, you could say it's true for all n, but I'm just going to say it's good enough for n greater than or equal to 1. The second thing is that we want to show u sub n is a decreasing or non-increasing sequence. Now, this is going to be greater than or equal to the following. Now, be careful with this step. Why is that true? Why is that bottom inequality true? Yeah, I guess if I wanted to justify this, I would write a little comment. Something like that. And there's one last thing to do for the Leibniz test or alternating series test. Show that u sub n goes to 0. Okay, so as n gets large and positive, the bottom's going to get real large. So that definitely goes to 0. So we can now apply Leibniz test, aka AST. The alternating series test. To conclude, our series in star must converge. Questions? Questions? Yes? Sorry, say again? For that one, that series isn't positive. So you might be able to take absolute values and show that it converges absolutely. Sorry? I mean, the way, if you wanted to use a different method there, I'd show that it converged absolutely, right? And then, I mean, and you could do that by using the integral test if you wanted to, okay? So you could do that. Any other questions? Yes? Yep. Don't skimp on this, okay? Make sure you explain the 3 points. Okay, so that's a little bit on series. In part III, we're asked to formulate some Taylor polynomials and look at some errors in the polynomial approximation. So let's have a look at that. So the first question is, write down the second order Taylor polynomial for e to the x. So just bear with me. So, Maclaurin polynomials, right? They involve derivatives of the function at 0. So for this one, we're asked to calculate the second order polynomial, right? So the Maclaurin polynomial of order 2 is just the following. Okay, it's f of 0 plus f prime of 0 times x Now I haven't written the factorials in, but hopefully it's clear. So all I need to do is work out all those derivatives at 0. Now it's pretty easy. F of 0 is going to be 1, f prime of 0 is going to be 1, f double prime of 0. Oh yeah. So this is going to be, and in fact the question actually asks you to write down the Taylor polynomial. So I don't actually know if you need to go to that length. You should just write it down if you can. Okay? Now the second part of this question says, use Lagrange's formula for the remainder to estimate the maximum error in approximating the function by this Maclaurin polynomial on this interval. So this is slightly more involved. We have done one of these in lectures, if I remember correctly, but it's slightly more involved. So let's have a look at this. Actually, I'll take a new page for that. All right, so Taylor's theorem tells us the following. Any function that's differentiable enough can be written as Maclaurin polynomial or Taylor polynomial plus an extra bit and a remainder. What we want to do for our particular f is estimate the remainder. Okay? So what is this remainder? Now in your class notes, in the course pack, there's a 3 down there. I don't like that, so just be aware of this. So no matter what you define, how you denote the error or the remainder, it's still the same, right? Now C here is a point between 0 and x. Now we don't usually know what the point C is. Okay? We don't know what C is, right? So that doesn't hurt it. It doesn't hinder us, right? We can still get some information without knowing what C is. And here's the key. X is, in the question, right? X is between -1/2 and 1/2. And if C is between 0 and x, C's got to be in this interval as well. So what we do is we do our calculations with x between -1/2 and 1/2 and C between -1/2 and 1/2. That'll cover everything. So how do we do it? Now, if our f of x is e to the x, then our remainder up here is just e to the c, x cubed on 3. So, we have the following. So all we have to do is form some sort of inequality on this, right? So on the bottom I'm going to get something like 48. And what I can do now is, you'll have calculators in your exam, right? I can just take out my calculator, punch in the square root of e, and divide by 48. And then rounded off to 3 decimal places. Okay, so you will need your calculator at that point. Questions? Okay. All right, so that's 3. Let's go on to 4. Now, 4 is probably the hardest part on this paper of the calculus questions. It involves a power series. A power series. Now, the dangerous thing with this question is you look at it and you go, oh, that looks really hard. But the series, the power series we use in this problem is nothing more than the geometric series. Okay, geometric series that you would have seen in grade 11. Okay, a geometric series. So this question's kind of cute because it kind of relies on a really, really basic series. So don't worry about copying this down. I'll put it up when I post. All right, so part IV. Now, the first part of this question is, given that power series, what's the largest open interval of convergence? So what they're asking to do is apply the ratio test to this problem and find some sort of open interval of convergence. You're not worried about the endpoints, even though we know how to test them. We're not worried about that. You don't have to do that for this question. They don't ask you for it. Okay, so let's just apply the ratio test and come up with some sort of open interval. Now, for this particular problem, because I've got an x to the n minus 1 here, I'm going to let Cn be the following. Now, in the other solutions I've given you in class, usually what I do is I consider Cn x to the n. Here I've just let Cn be everything because that n minus 1's a little confusing. It doesn't change much. So let's just clean up the algebra a little bit here. So now what we want to do is look at the ratio of Cn plus 1 over Cn, absolute, right? If that limit is less than 1, then we can build, well, where that limit's less than 1, we can build our interval of convergence. So consider, please. Now we need absolute values here because our ratio involves x. We don't know whether x is positive or negative. Okay, so let's see if we can take this limit and simplify. Okay, so it's a bit of a mess, but we can cancel. We can do a lot of cancellation here. So firstly, the x's are going to cancel down to absolute x. It's got nothing to do with the limit, so let's take that out the front. And I'm going to be left with, okay, the two n's are going to cancel. I'm going to be left with 2 n plus 1 over n. And because n's large and positive, I can get rid of the absolute value signs. So the limit of this part is going to be 2, right? So what I want to do is force that limit to be less than 1 and find the x values. So what x values are going to make this inequality hold? X between what? Right, a half and minus a half, right? Or minus a half and a half. So by the ratio test, the series converges there. And this is the largest interval of open interval of convergence. So let's name our test. So let's give this a label, star, you guessed it. Okay, so well, who cares? What have we actually found there?
So it converges between the values.
Yep. So that's the largest open interval, the largest open interval. But what have we found? How does this relate back to our function up the top, our f of x or f? What have we found here? Any ideas? I'm confused. Do you know? Huh? Me, Jedama? Huh? Huh? We found the domain of f. We found all the x values that give that starred function, or power series, whatever you want to call it, meaning, okay? Yes? What's that? Well, the thing is you can't do much with it, okay? Yeah. So if you put in, say, x equals 1, what can you do? So there's not much. So for example, divergent series won't obey, differentiation, integration, the rules of algebra. Okay. Right. So not too bad that question, but it gets a little bit harder. Here, big f of x is defined as the integral of little f from this interval, 0 to x. Write down the power series for big f of x. So essentially all we really want to do there is take what we found in A and integrate it. Integrate it. So this is A. Okay. So if big f of x is defined as the integral of little f, and you may think, well, what's going on with the t there? The t is just a dummy variable, okay? It doesn't change anything at all. Let's work out some power series for big f of x. Now, so from part A, we're going to replace little f with its series we got in A. Now I just need to be a little bit careful with my variables, my letters, because it's little f of t. I need to change my x's to t's from part A. So what do we do now? I've forgotten. Yeah, just switch the summation sign and the integral sign. We can do that because we know that this series converges. Now, here, so we're going to switch these over and then integrate. Now, it's very important to remember here, I'm only working in the interval from part A, so minus a half to positive a half. Outside of that interval, you can't just switch these sum and integral signs. So let's go through and integrate this. Well, so if I integrate, that t to the n minus 1 is going to go to t to the n. I'm going to divide by the new power. So I can cancel that off. And when I plug in x for t and 0 for t, I'm going to get the following. So throughout those calculations, I'm keeping x between minus a half and positive a half. Okay? Now, does our answer look kind of familiar? What kind of series is that thing in the sum in the corner? It's geometric, right? It's a geometric series. If you just write this is 2x all to the n, it's a geometric series. So we've calculated our power series. Let's have a look at the part C. By summing the series in part B, express big F as a simple function, not as a power series or a series. So what we have to do is work out some simple representation for this. That's all we have to do. Now, it's a geometric series, and we know how to sum geometric series, right? So that's kind of handy. Right, from B, we have the following. Now, if I just write this another way, so that's a geometric series, not in x, but in 2x. There's something a little bit funny also about that series. Note that the sum starts at n equals 1 rather than n equals 0. So we've got to adjust for that as well. Okay? So this question isn't hard. It's just there's a couple of little things that can trip you up. So let's just write down the basic geometric series. What does this converge to? This. What does it converge to? 1 over what? 1 minus t. Huh? There's a couple of ways. You look at the partial sums. It's something you should know. Okay? Grade 11. But you can. This is something you should know. You should know what a geometric series converges to. If you don't, you need to know it before the exam. Okay? Now, if you want to verify that, you can just look back at the lecture that I gave on this and show how I looked at the sequence of partial sums. All right, so what does it mean for this? Double star. Now, firstly up here, this is almost the same with t equals 2x, but the starting position is different on the end, so you've got to bring 1 to the other side. Okay. And again, we're staying within the interval of convergence. Okay, so not too bad if you know what a geometric series is. Part D, hence find little f of x as a simple function of x not involving a series. So remember, look at the relationship between big F and little f. If you differentiate this, you'll work out that big F dash equals little f. So all I need to do is take this and differentiate it to get little f. Okay, by the fundamental theorem of calculus, big F prime's got to equal little f. So all I need to do is differentiate in here, and I'll get little f. So let's just differentiate each part of this. And according to my calculations, you get something like this. Okay, so now you can see why that's potentially the most challenging part of the calculus. When you think about it, it just comes down to fundamental theorem of calculus and a geometric series. Questions? Question? No? Oh. Okay, so the last one. Find the arc length of the curve described by these parametric equations for t between 0 and pi on 2. Now remember, for arc length, there's a formula for it. It involves the integral of a certain square root. So let's calculate the derivatives of these functions, square them, add them together, square root, and then integrate. The challenging thing here is to manage away the square root sign in the integral. That is the challenge. So all right, so I'm going to just let my notation be the following. And t here is between 0 and pi on 2. So let's calculate the derivatives, square them, add them together, square root, integrate. So let's just remember the arc length. Now, like I said, the challenge is managing the square root sign away. Sometimes it's easy, sometimes it's not. So let's differentiate component-wise. So it's going to be something like minus 12 sine t cos squared t. And y prime is going to be something like 12 cos t sine squared t. Now, it's looking like a bit of a mess. When we square those, it looks like we're going to get something more complicated, right? But in fact, things are actually going to work out fairly nicely. Okay, so let's just square these. I'm going to get 144 and 144, sine squared cos to the power 4, cos squared sine to the power 4. So I should get something a little bit like this. All right, now it's looking messy, but what I'm going to do, I'm going to pinch a cos squared out of the first term in that big bracket. Actually, things are going to simplify quite nicely. So I'm going to split that up into cos squared, and then change the cos squared to 1 minus sine squared. Now when you expand that, you're going to get some nice cancellation. So the square root of that is going to be something like 12 sine t cos t. You don't have to worry about the absolute value signs because you're integrating from 0 to pi. Both functions are positive there, or non-negative. So the square root of this is just going to be something like 12 sine t cos t dt. Go to a double angle formula. Okay, so moving on. So if you integrate this now, you will, I'm not going to do all the details, you'll get 6. So the arc length is 6.